Hi, this is Lester Martin from Hortonworks University, and we're going to continue on in the Hadoop Essentials course. This next section is called Apache Hive. The quick objectives we'll focus on here, again, is to present an overview of Hive, and for the most part, most of us know a lot about relational database management systems. So we'll look at it from those eyes and try to compare and contrast the differences and the things that are the same in Hive in your traditional databases. Definitely review the architecture. Go through some straightforward operations that you'll need to surface data as tables and hives, and views in Hive, and then we'll talk through some of the performance improvements that have been done to date and some that are also ahead of us, and we'll finish up with a demonstration. So what is Hive? A lot of people refer to Hive simply as the data warehousing system for Hadoop. There are other technologies, but I think Hive is the most mature, the most widely used in that concept, under that name. And Hive, for the most part, represents logical tables to data that itself is sitting somewhere in Hadoop. Somewhere means some different location, and more than likely it means some different file format as well. So we'll make sure that information gets surfaced up into Hive so folks can make connections, run typical queries using standards like SQL 92. I would not say Hive is perfectly SQL 92 compliant, but it's a drive towards SQL compliance in many ways. There are just some things that we can't do or will not do, but the vast majority of that standard should be applicable for Hive. And the goal really has been to build interactive queries. Hive's history obviously came out after MapReduce, and we were looking for opportunities to express MapReduce into a framework, into a language, etc., that other folks could easily consume, and SQL surely was that. So that was the focus initially. So initially, speed and all that wasn't the driver. It was just to be able to calculate results. Fast forward a number of years, and we are focusing very heavily on high performance. And again, we want folks that know SQL already to almost out of the gate know Hive, or at least know how to utilize Hive once Hive is properly set up, tables are defined, etc. That's a different set of skills to learn how to do the behind the scenes, but definitely the consumption of things that are presented in Hive should be very familiar from not just the data types, but the different types of queries, analytics, etc. that you see kind of listed on that right-hand side there. So for the architecture itself, on the far left here, we have our normal, customers, clients, connections, whatever that makes the most sense to you, and the tools that we offer, definitely a command line interface, but more than likely, and definitely as a human driving queries individually, offer up a web UI that I'll show you. But many times what we're thinking about in Hive is people with ODBC or JDBC connections. Again, that could be a human, but it often could be a system as well. Those connections, regardless of how they work, really are under the covers going to talk ODBC, JDBC into a piece of software called Hive Server 2 or HS2. Now these green elements, you can arguably think of them as kind of the master processes that exist for the benefit of Hive. So Hive Server 2 maintains a connection with clients. Hive Server 2 working with this thing called the metastore that maintains the mapping of these logical tables to where the files physically are, what data types they are, etc. Works with that, works with the Hive engine itself, the Hive framework, the execution engines of MapReduce or TAS, and then basically the cost benefit, the cost based optimizer, etc., to decide, hey, what should we do? And once that decision is made, a job in classic terms would be sent off into the grid itself on behalf of this person that has a connection, and that could be run at scale on this large cluster along with everyone else. So the real processing is happening, the orchestration of what needs to get done, the planning is happening in our master services, so the Hive-based master processes, and then they're going to be submitted out into the grid as a whole to run with alongside everything else that's out there. So that's the quick high-level architectural view. So consuming Hive should look like consuming typical databases. Most databases have some kind of command line interface. We surely have that as well. Databases, many people have their own GUI editor, DB visualizers, the Toads, the SQL Anywhere. Those different technologies that you have out there, definitely you can use those. And they're not just limited to SQL tools. They may be some kind of hybrid BI tool that allows you to make connections, etc. So a variety of GUI tools. And then definitely in Embari, we support a concept called a view, an Embari view called simply the Hive view, where you can interrogate the tables, run queries. Again, see the underline explains, etc. And we'll see this in the demonstration as well as the Embari Hive view. So yes, it's out there. You understand the rough architecture. You know how to access and run queries, etc. But how do you prepare information? How do you define information in such a way that you can consume it? Well, we use classic data definition language, create table statements that, for the most part, should be something you understand already. I like to think of these concepts as the above the line and below the line. So everything from create table, the table name, and then all the column types, those are what I would think of the classic above the line. Very straightforward. Now the things that you see past that, I'll call them the below the line, are really focused on where is the data that this table is supporting, is fronting, or presenting, and how is it stored? What kind of information is it? Is it a comma separated value list? Is it an ORC file, an Avro file? What is that physical file format? And this is a very simple example, and even the ones I'll show you in the next slides are relatively simple, but depending on how complicated or sophisticated that underlying file format is, there could be several lines of details here that really help Hive understand that information. Again, that's from the engine needing to define information. So this slide and the last slide really look the same, except we introduced this word called external, and I made sure I threw it in there because I think a lot of people, when they think about Hive, they kind of can get that Hive as a front end to data that sits on this large file system, HDFS, and they get a little interested, and then there's this concern about Hive, quote unquote, owning the underlying tables and files for those tables, and a lot of people are concerned that maybe I'd like to make sure information is consumable by other tools and technologies. And you can do that with and without this notion of external tables. So external tables, really, what they really come down to, the primary driver here is that when we declare a table external, we decouple one action. When we drop a table with a managed table or a non-external table, the Hive engine will tear down and delete those underlying files. If we mark a table external, then if we drop a table, the data that table's backing is going to be left alone. And it's about as simple as that. If you've heard that phrase external, or if you heard internal, I'll use managed tables, and or just tables and then external tables. So external tables will not drop data, will not delete data on a table drop command. And then lastly, on this theme, I'll throw out location. So if you've heard a little bit about external, most people say you have to declare where that data is going to reside at. That's backed by that quote-unquote external table. Well, in all reality, Hive has to know where to store, again, where is the data. Hive uses a default directory of apps Hive warehouse to store tables and databases and tables if you don't tell Hive where to store them. But so you can very specifically declare location. Now, the reality is 4 out of 5, 9 out of 10 times people that use external tables will almost always use a location. But I'm going to make the point that those can be intermixed. They're not coupled together, and external has to have a location. External can use the default location, which is the apps Hive warehouse, and then apps and a managed table, in fact, could be have the information sitting behind it somewhere else in the file system, if that makes sense. So tables, external tables, and then very explicitly being defining where the physical files reside on the file system are a pretty common theme and coupled together. So we have the table definitions, and we could do a show tables. We could do we'll do these things in the demo. We could do show tables, describe tables, etc. But if we did a select all from these tables, they're going to be empty. There's no data in them. So two classic, simple, easy ways are just use kind of the front door commands, load data into said table. And these two commands, the real difference is that data on the local file system, or as in the second example, is it in HDFS proper? So nothing too complicated there. Or we could use kind of an insert into concept. So if we had a predefined table called birthdays, as long as we have a query that whose metadata, columns, names, types, etc. all line up well with birthdays, we could actually do an insert into a birthday based on some results of another query. We'll also see in the tutorial that the demo that we can do a concept called a CTAS, a create table as select, where we actually do the DDL and this notion of an insert into in one operation. We'll create a table as, and then we'll just define the select statement we want, and all that metadata, column names, etc. will go into the definition of the table itself. Running queries. The good news is, I'm not going to sit up here and talk to you about explaining how to run a query. I'm expecting and assuming that you have that expertise and skill sets. And this is just trying to point out, as I said at the very beginning, running a query should look like the same in Hive as it does in a database, a traditional database. The differences are going to be behaviors and how things respond or don't respond. The traditional open source or commercial off-the-shelf solution, managing a couple hundred megabytes or beyond, a couple gigabytes of data sets, historically it's extremely blazingly fast. Hive itself, sits on Hadoop. Hadoop is a big engine looking for big data. And those smallest of trivial data may in fact run faster on that SQL system, but we would expect massively the difference, larger and larger and larger data, to the point is where we can only run queries in Hive that probably just can't run. We can run queries out of Hive that possibly won't even run in your relational system, or maybe you can't even store that kind of data. So again, running queries are going to be what you're used to. What is going to happen behind the scenes? Well, the reality is, we talked about earlier this notion of map and reduce and how that's the foundational parallel processing either engine or concept, and those concepts and that engine itself and then other engines that use MapReduce are at play here. So where things that are part of your query that you can imagine, if I'm looking at slices of my data set, I can work on those, in parallel. Select, give me this column, that column, etc. Those are happening behind the scenes in this map phase, but there are definite key statements you're going to ask. Join is a great example where really we have to kind of resolve this information and finalize the answer, kind of aggregate it in this reducer phase. So this is all going to happen as a reducer side function. Some more advanced topics to not get into where we can truly do some different concepts even on joins that happen up in the map phases if data sets are sized appropriately, etc., that we can discuss. But for the most part, this is a fair conversation here. And even other activities, order bys, distincts are great examples that have to happen in the reduce phase. So just trying to make that point that we're thinking in SQL, but SQL, we're using a framework that takes your SQL and creates a job that can run in this parallel processing engine that we call Hadoop itself. Another topic is views. I want to make sure we threw out there. So Hive does support views, but Hive does not support materialized views, which is an option that most databases have. So Hive, for the most part, we're just defining a query and wrapping that with a view. And when we ask questions like show tables, etc., we expect to see the views listed alongside the tables and look and smell and act like, from the consumption side, the same thing as a table. How do you define one? Create view, the view name as, and define that select statement for us. So this is a way, in fact, we'll see much later in the course when we do introduce Ranger and we talk about some security concepts and policies. I will show an example of using a view to create the equivalent of a row level permissioning model where maybe some group can see these specific rows but not those specific rows. So we can manage that via views a little later. So very simple to create, and then once they're created, very simple to run a select statement on them. So again, that visitors is already a complicated, well, not complicated, is a non-trivial but not overly complicated query. And then we think of it as a table and apply more constraints, etc., to get the information we want. Now, if you look really closely, I left in this query in an interesting format, a scenario I see unique, at least in my perspective, to Hive. Hive allows us to play this kind of flip our select statements. We can declare our froms and then go into the select. And I left it out there because there are some folks that still use that style, and I want to make sure you saw it one time in case once you go off in your additional learnings, you notice something like that and had a question. So as I mentioned earlier, Hive grew out as a framework that sat on top of classic MapReduce to simplify that programming model to something that many people could easily consume. In the initial, if a MapReduce job took 20 minutes to get that answer, then we really didn't expect Hive to, be much faster or much slower. We expected it to be very equivalent to what the output would be if we wrote it in MapReduce. That was the whole concept. It was just to bring something simpler programming or analysis model to MapReduce itself. But obviously, anytime we put something with SQL on it, we start tying front ends against that, and BI tools, reporting engines, etc. Performance is always on the tip of the tongue, and then moving on. So I want to talk about this notion that we've called historically Stinger, and then an initiative past that in just a second here. So the Stinger initiative took us from some of the earlier days in Hive and really did some, foundational things, some in-memory, some joining concepts, some base optimizations, definitely adapted to Yarn early on, and some of that is foundational things, especially the Yarn side of the house. But probably some of the key improvements that the Stinger initiative gave us are in that second tier and the third tier here. Definitely, we created an execution engine, primarily and initially for the benefit of Hive. Other engines now, other frameworks like Pig can take advantage of, and beyond can take advantage of Tez. But Tez is ultimately, I'm going to show you in just a moment an example of comparing and contrasting Tez with MapReduce. It is a MapReduce in concept engine, but maybe without all the constraints that MapReduce has. So Tez as an execution engine, definitely a file format improvement called ORC. It's a columnar store, a lot of compression opportunities, a lot of opportunities to really couple an execution engine plus Hive plus this file format to get massive lift and changes. And then just things in the engine itself, the notion of vectorization, where instead of looking at a row by row by row, I don't get a large bulk of or a vector of information and run it on batch. So a lot more looking ahead that wasn't in classic parallel processing, classic MapReduce. Work on a little bit at a time. So it's very simple stuff. And then implementing, a modern database mindset, this notion of a cost-based optimizer that really wasn't initially in Hive. So what we really did is we tried to make Hive in many ways act like a relational system, have a really a customized file format, optimizers, etc. So massive improvements in that space, and that finished up around the Hive 13 time. And post that, we focus on this next initiative called Stinger.next. So you kind of see the batch move to interactive. The real push now is this phrase sub-second. Now, I don't think anyone's suggesting Hive's going to be sub-second response time on any and all queries in the world, but definitely in queries that we tune, we understand, we configure, we really want certain data sets to really respond dramatically and fast. There's a lot of effort there. Bring some additional master services out there. Bring some additional caching concepts, which is always a way to help things go faster. There is in today Hive this notion of insert, update, delete statements, and even a transaction that spans, unfortunately, only one operation. So there is a lot of effort in taking those DML type operations, demarking those with wider transactions. So much effort in there. We want to go beyond SQL 92 into the richer, even further. There's quite a bit of analytics SQL in Hive today, but much more rich desires and spaces there. And then just like we went and introduced this TES as an execution engine option instead of just MapReduce, there is an effort underway to bring Spark as a third execution engine option underneath Hive. So that's some activity there. Let me just kind of precursor for our Spark conversation later. That's different than Spark SQL. This is using Hive and then letting Hive under the covers look at Spark as a possible execution engine. So before we wrap it up, I did want to take a moment and run through maybe some high-level differences or high-level improvements that TES gives us above and beyond classic MapReduce, the true MapReduce engine that we all started with in Hadoop. So what we're trying to show here, and I'm not trying to edit check this, what we're trying to show is maybe we have a somewhat mildly complicated query with some joining going on. And what that means on the left is, in the day, Hive decided 4 different MapReduce jobs ultimately have to be executed to get to the point where we can return those results to the consumer. And when we run that in a Hive engine, to be honest, that the map and reduce phases as a concept still are present, but TES has the opportunity to kind of decouple and step away from some of the formal constraints that the MapReduce engine had implemented originally for very good reasons, and move on and march forward. So I guess 2 points I want to call out is that MapReduce is defined at a job. So we may run a query that runs 1, 2, 3, 4 jobs. So we wait to the end of all that, but a job finishes, and a job has to output its data on HDFS. So if that's some quote-unquote intermediate data for the whole query, we are taking a little bit of a hit to write that information off to HDFS to turn around and then read it into the next step and read it into the next step. So TES lets us step away from that constraint, especially when we see as a builder, a framework that's using TES, that we need to do many other things. We can post that information a lot more local, so possibly totally in memory, possibly just streaming. But even when we write to disk, we don't have to incur the slightly additional cost overhead of writing to HDFS for long-term durability and reliability. So that's a huge lift. And then just one more real concept that we see, if you kind of notice, there are some boxes over here that we just don't have a mapper phase in front of them. That's going to happen, and there are going to be some times when in the MapReduce engine, well, you know what, I really need to do just the reduce phase, but we don't have this concept of a reduce only job in MapReduce. We have a map only, but not a reduce only. So if we stop the process of requiring us to go through that phase, then we also, in fact, miss the process called the sort and shuffle that we discussed earlier. And overall, those two improvements, there are others. There are many other things that make TES different than classic MapReduce engine, but those are the two that I think a lot of people can understand very quickly and can see how those changes could make a significant difference at runtime. So we'll take a quick knowledge check and see what we covered here before we go into the demo. And there we go. So maybe what will be the back at the architectural slide? What element, what component in Hive do clients using ODBC, JDBC? What do they connect to? And that was called Hive Server 2, is the main place that maintains those sessions, those connections. And we just talked about this one, so I think you get at least one on what are the execution engines that we can, that TES can use, that Hive can use. Well, I just said one of them TES, the other one's MapReduce. And that's as of HTTP 2.4, that's our option. Sometime in the future, most likely, Spark will also be introduced. And primary difference between an external table and managed one. I kind of harped on this one a little bit. I think it's really about a managed table, when dropped, will delete the underlying data that it fronts, and an external table will not do that. So just a coupled question, true and false, that a managed table can actually store information, can use the location keyword to put that information somewhere besides the default AppsHive warehouse. And that is actually true. It can, but I would say most people, again, 4 out of 5, 9 out of 10 folks would actually store, would use location along with external. But you can mix and match. So if you took a quadrant for compartments, quadrant, that all the different options are possible and available to you. And we just talked through some of those Stinger initiatives. Definitely one of those was TES. There were some earlier just base improvements of how the engine can work. Definitely we introduced Yarn in that transition. TES is an execution engine, ORC file format, and then just some acting more and more like a database, vectorization, and cost-based optimizer were the real key lifts there. So on the screen are just a quick summary of the things that we covered in a short introduction and overview of Hive. And we'll move on and perform a demonstration manipulating some data with Hive.